So likewise, this is going to be a real whirlwind tour over unsupervised learning. I understand that this topic was put in the queue based on popular demand. So I don't know. Unsupervised learning is a gigantic topic. It encompasses a whole lot of different methods and ideas. Again, I'm going to take it at a very, very broad level. And if you all have any specific questions, maybe when this topic emerged, there was some specific questions in mind, don't hesitate to stop me and ask as we go through this. Kind of want to try to make this a discussion if possible. But until then, I'm casting a pretty broad net. So I'm going to start with just a reference point. So all the techniques Kyle talked about, for the most part, regression and classification, all fall into the supervised learning regime, which I assume everybody's probably mostly familiar with. But again, as a reference point, I'll just lay it out in the most essential details. So you've typically got some data, just say images of shapes and some labels. In this case, just indicating whether it's a circle or a square. And through some training process, you want to get a model that can, when given a shape, produce the correct label. So the goal is pretty straightforward. In all these cases, you have some target that's given. You want a model that's going to predict a label, or connecting it back to energy applications. You want to know the capacity of the solar panels. You're trying to make a model that's going to predict that accurately, or the energy consumption of a building. And so the goal's pretty clear. If we step forward, so in unsupervised learning, you don't have the labels anymore. And you have this kind of very, I would say, vague prompt of find structure or patterns in a set of data. So that's where things get really broad. And so finding patterns and structure can mean a lot of different things, and it does mean a lot of different things depending on what type of technique you're looking at. So I'll give one example to give you some intuition, and one which I think a lot of folks are probably familiar with, but is clustering. So taking the same shapes example, and I'll just, as a quick aside, I really had grand ambitions for this shape example. I couldn't find anything on the internet that I liked, so I had to craft my own. And I had this vision of just laying out all of unsupervised learning using this simple shape example. I think it was a little bit much, but I got a lot of runway out of this. So that's where this came from, in case anybody was wondering. So anyway, back onto the story. You've got the shapes again. So these are imagine little images of shapes, and you want to cluster those into groups based on how they're similar. So that's one sense of structure, is grouping them up into clusters where each cluster contains data that are similar in some respect. But this is a common problem in unsupervised learning in general. You don't have a clear objective. So there's many different ways you can do this. So here I've shown three different clusters that I think are all three different ways you can cluster the data that are all plausibly correct. So on the first one, I've clustered it up by color, and the second one by size, and then the third one, whether it's a circle or a square. So which clustering is best? Well, the one on the far right happens to correspond to the labels of circle or square that I had before. But if you're just given the prompt of, find structure in the data, that doesn't necessarily have to be the correct way to do it. And so this is a big theme in unsupervised learning. Next slide, please. So there's no right answer. And generally what happens is, for a lot of unsupervised learning, you kind of assume some criteria for what constitutes a correct answer. So you say, I want to cluster them up based on, shape or color, for example. You could pick one. And then you try to find the clusters that sort of fit that criteria as best as possible. But in most cases, the criteria that's chosen is sort of arbitrary. So you don't really know whether it's correct in any general sense. But you hope to discover some structure that might be meaningful to you in the data. So next slide, please. So just giving an even more concrete example. So this is Gaussian mixture clustering. This is a pretty simple example of a clustering algorithm where you say you have some data. The features are x2 and x1. So this might be like the height and area of a building, going back to Kyle's example of finding the building footprints and estimating consumption. So you've got some data like that. and you want to cluster the building. So one way to do that is to just assume that the data was sampled from two Gaussian distributions. So two Gaussians, each with its own mean and maybe equal standard deviations. So one clustering algorithm, so Gaussian mixture clustering, works by basically saying, I'm going to assume this data was coming from two Gaussian distributions, and I'm going to try to find the Gaussians that, if they existed, maximize the likelihood of the data. So what that amounts to is I'm going to move these little centers of the Gaussians around until they kind of fit over the data. And then if those were the Gaussians generating the data has a very high likelihood of having come from those Gaussians, if that makes sense. So again, if anybody has questions, this is a pretty fast exposition on Gaussian mixture models, but hopefully the general idea is clear. So once you get done fitting those, sorry, Kyle, real quick back. So once you get done fitting those, the clusters that you get correspond to the means of those two Gaussians, and you just say those are two kind of clusters of data that have similar features to them. All right, we can jump. Okay, so that's just one assumption you can make. The data comes from two Gaussian distributions, but there's a whole lot of other different assumptions you can make about the data, and from that you can get a lot of different algorithms. So I'm going to illustrate these here in a second, just some popular ones, but what's shown here are a number of different data sets similar to the one I showed before, just different structures in the data, and again, two feature dimensions there. So one step forward, please. Oh yeah, thank you. And let me move my first bar. So what you're looking at are four different popular clustering algorithms listed up there on the top, applied to each of these data sets. And so some of these may be recognizable. K-means, Gaussian mixtures is the second one. That's what I just discussed. Agglomerative clustering and DB scans. So these are all pretty popular in the literature. You'll find them popping up from time to time. And you can see if you look through each of these data sets, each one of these clustering algorithms will give what is an intuitively satisfying clustering, though not necessarily correct, as we said, because they're all kind of arbitrary at the end of the day. But if you sort of follow your sense of what makes a good cluster in each of these cases, you'll see that each of these algorithms works well in one case, in at least one case, and fails in at least one of the other cases. And that's kind of, again, the theme that I'm going to keep hammering on with unsupervised learning, is that ultimately they give different answers and they find different structures based on the assumptions of the model. And you have to understand those assumptions in order to really make sense and interpret the results that you get from them. So next slide. Yeah, so just taking a pit stop, I'm going to talk about some more unsupervised learning techniques quickly, but before leaving clustering, just a few notes on when it might be used. So typically it's used for data exploration, so you can group up your data into clusters of sort of similar along some criteria groups, or groups of data instances that are similar, and then inspect them to sort of gain some insights about what features are sort of most distinct in your data sets. Data partitioning, this is another common way of using it. You can break up, sort of take a complex problem where you have data that sort of very heterogeneous in its features, and split it up into smaller groups that you can analyze separately. So maybe a linear model wouldn't work for all of your data, but if you split it up into little subgroups, into clusters, then you can sort of fit a mean or a linear model to each of them. And then feature extraction. This was pretty popular in the pre-deep learning era, but you could use this to extract features in imaging. So again, I realize this might be a little bit vague, but hopefully give you some sense of how some of these techniques are used, so you can dig in further if you think they might be applicable. Next slide, please. So what I've listed here are a number of unsupervised learning tasks. So there's more than what's listed here, and these are some of the major ones that are out there. I already talked about clustering, and I'm gonna just touch on dimensionality reduction and generative modeling as two big ones quickly here, just to again give you a sense for how these are used. Next slide, please. So So in dimensionality reduction, the goal is typically that you have some high dimensional data. So maybe, you have maybe some features quantifying the behavior of energy usage in households or something like that. And you need to sort of try to understand that data by visualizing it. And so to do that, you want to maybe map it down to some lower dimensional space, some key features about that data, basically, that you want to extract, then that you can sort of visualize and see how the data groups up. So that's often the goal of dimensionality reduction. Can you click forward, Kyle? Yep, actually two. So going back to the shapes example, so you may have some data that's, again, set of images of shapes. Those images, although it's not obvious to the eye because humans are so good at interpreting images, but an image like these of shapes is very high dimensional. So you've got three color channels, and then maybe 20 by 20 pixels each one. It's very, very hard if you don't know what you're looking at. So these are shapes, so it's very easy to see, kind of extract some structure from those. But imagine you're looking at like molecular bonds or metamaterials like Yang's looking at them. Becomes harder to make sense of high dimensional data. So what you might do is extract some features from those that capture the key attributes in the data, the key factors of variation. So I've already kind of done that here, and I've labeled them too. So this is a three-dimensional compression of otherwise very high-dimensional data, where you've got shape, color, and size there listed in a numerical representation. And once you sort of map it down to that low-dimensional space, it's much easier to visualize it and then make sense of the data. So this is, again, primarily used for visualization and data exploration, and sometimes this technique's incorporated into learning algorithms. I've listed some examples there. Next slide, please. And I think just for the sake of time, I'll go through this really quickly, but here are some popular dimensionality reduction methods: UMAP, TSNE, and principal component analysis applied to some big data sets. So I'll just quickly point out, so along the columns, there are three data sets, and they're very high dimensionality. So I put that up there. And I'll just point to the one in the middle, which is IMNIS, which are pictures of digits, numbers. So these are 784 dimension vectors that you get. That's all that the algorithm sees. And using UMAP, for example, the first row, it can automatically map it into 2 dimensions where the numbers all cluster up and you can easily see the structure in the data. It's very, very cool. There's a lot of really great examples. If you dig into some of these other data sets, you'll see it's just pretty amazing what this can do without knowing anything about the data set. You literally give it these giant vectors and it can cluster up the data. And I put the labels for the numbers on there so you could see that. So sort of the red ones on the right. I know you can't see my pen, but like this one here. It groups all the zeros, pictures of zeros, all up into its own cluster, and same with the other numbers. So these are very powerful techniques, especially I'm a big fan of UMAP, but everybody might have their own favorite. So next slide, please. And then the last one I wanted to touch on, which is a big one, is generative modeling. So the idea here is that you want to, in most cases, though not all, this is, again, these are very big topics, each one, but you want to fit a probability. You want to learn the distribution of the data that you're looking at. So that often entails fitting a probability distribution to the data. It's very much like the mixture modeling that I talked about a few slides back. In this case, I changed it just a bit to sort of illustrate how it's distinct. But in this case, you might have some data, again, unlabeled. You don't know anything about it. And what you're trying to do is basically try to model it with a probability distribution. In this case, just say it's Gaussian. So we fit a little Gaussian distribution, the means labeled there. And once you have that distribution fit, and if it's a good fit, you can do things like sample unique new instances of that data, or you can take a new data point and detect outliers by saying, how likely is this data point to have been coming from that distribution, from that Gaussian? Next slide, please. So I list out some of these use cases here. So generative modeling is, it's used in so many instances. And so I mentioned a few of those: generating novel data samples. Outlier anomaly detection is a big one because you can calculate the likelihood of new data points and determine how likely, how unusual they are compared to the data you've already got. Some others that are a little harder to unpack here, but inverse modeling. This actually ties in with Yang's work, with which I'm quite familiar. And you can use this also to sort of regularize supervised learning models, where you tend to keep them from overfitting to the data that you've got if you're looking at supervised problems. Okay, next slide. And one other really compelling example that I can't go without mentioning is these generative models. So these generative adversarial models. So these are relatively recent phenomenon. They are generative models, but they are not probabilistic. You're not actually fitting a probability distribution to the data. But despite that, these work really, really well. So what I've shown here, this is work, I think it was from NVIDIA a few years back, where what they did is they built a model, which I've labeled the generator, and it takes random numbers. So you pop in a random number and the generator generates a new sample from the distribution of human faces. What I've shown is on one of these two sets of faces is not real. It's actually generated from this algorithm. And I don't know about you, but it's very, very hard for me to distinguish which of these are real and not. So these algorithms are getting really, really good. And this ties in with all the deep fakes that folks may have heard of. This is a very interesting and fast-paced area, and it's getting pretty impressive. And just for reference, the top images are the fake ones in this example, although I had a very hard time telling. So next slide, please. So I think that's it. That's about as much as I'm going to be able to get in here. A few concluding remarks on this. So as I said, unsupervised learning is a massive field. All the references and texts that Kyle shared will have chapters on unsupervised learning, and you could take a look there. I really wanted to try to give you all a sense of what some of these things do and how you might use them, and just point out that when you're using them, it's very important to understand the assumptions that they make, because as I said, they each make different assumptions. There's often no clear right answer of what assumption should be made. And so the most you can usually do is just be very aware of how that model is seeing the world and use that when interpreting the results it's giving you. And maybe the last point there, the middle bullet, is that you generally want to use these techniques when you have large quantities of data and maybe not labels for the data yet. So either labels are hard to come by, they're expensive to get, or you don't necessarily have a goal in mind. You just want to explore the data and find structure in it that may not be obvious.